I'm actually a little confused. It's actually kind of weird, but it says running in the sidebar. Okay, cool. Anyway, I'll get started. Hey everyone. I think I'll wait for a couple more people to join before I start the first problem, just because there's kind of a set agenda for this stream. I'll just post here starting now. Stream. Weird. So for me, it says stream is running in the sidebar. Oh, but once you click it, it says stream will start soon. It's a little weird. D Beckham 18, thanks for the follow. Okay, now it looks like something's happening here. Cool. So I won't actually edit this. Instead, I will go back to the mashup. Cool. So while we wait for a few more people to trickle in, oh, X Crush Z, thanks for the follow. While we wait for a couple more people to trickle in, let me kind of get a brief survey of the people who are here. Of like, did you attempt the problems? Let's see if this link works. Cool. Yeah, so if you guys attempted the problems, let me know if you found them easy, difficult, maybe what your existing background in number theory is. I'm gonna try to cover what I think is a reasonable kind of middle point where I'm not gonna do all the basics, but I'm gonna try to explain any basics that are necessary for the problems. And also definitely if people have questions, just shout them out in the chat. But it would be nice to get a sense for kind of what people are looking to get out of the stream, just while we wait for a couple more people before I start the first problem. Let me just write this in the chat, waiting for a few more to join before I start going over a mashup. Cool. Let me know. Cool. I guess I'll try to get started now. Nice. I got a couple people excited in the chat. That's awesome to hear. Um, cool. Guess I'll try to resize this stuff a little bit. Thank you. Oh, yeah. Thanks for joining. How so too? All right, cool. This seems readable. All right, cool. So let's get started. I'm going to go over the first problem and then just go through all of them in sequence. Time permitting, of course. All right, so let's read this problem. And most of these problems I've already at least looked at, if not done at some point in the past. So this isn't going to be like solving from scratch. My thought was that it'll be a little bit more of an efficient use of time if it's problems that I already have a general idea of how to do and kind of outline. I'll do my best to try to outline the thought process that you would have when solving them from the first time. Though, of course, that's always a little bit difficult to do precisely. Cool. Let's check the chat. Okay, cool. So for the first problem, it says any even number greater than or equal to 4 can be expressed as the sum of two primes. Will it be available? Yeah, this will be available under the video section, and also I upload all my streams to YouTube, usually 1 or 2 days later, just because of it takes a little while. So you can check out my YouTube and watch things there. Definitely check out past streams, and I usually try to timestamp those videos so that it's easy to find the part that you're looking for using like the table of contents feature. Cool. So we're given n is greater than or equal to 12, and we want to have xy such that x plus y equals n, xy are composite. So my first thought upon reading this problem is we're looking to find something as the sum of two composite numbers. And it's kind of hard to check if numbers are prime or composite, but it's pretty easy to find a pretty big set of numbers that are composite. For example, any even number. I can actually type this part. No need to. So cool. So first observation, any even number other than 2 is composite. So 4, 6, etc. And then, so for example, if our number is an even number, we can do we can do 4 and n minus 4, which will both be even. And because n is more than 12, then they'll also both not be 2 or less, and they'll both be positive. So now that we have the fact that any even number is composite, then if n is odd, we're going to want to subtract an odd number from it to get an even number. So what's the first composite odd number? So 3 doesn't work, 5 doesn't work, 7 doesn't work, but 9 does work. Whoops. We can do 9 and n minus 9. So to check this, the smallest number where we'll have an odd number would be 13, since 12 is even. So the smallest case here would be 4, 8, and the smallest case here would be 9, 4. and 4 is a composite number, and then any odd number higher than this would be like 9 comma 6, 9 comma 8, etc. So that's basically what we want to do for this problem. So let's quickly code it up. So yeah, we just input n. So if we have an even number, we want to do 4 and n minus 4. Otherwise, we want to do 9 and n minus 9. So let's just check this on the samples. Cool. So these are 2 even numbers. This is 9 and an even number. Yeah, so this seems right. Let's submit it. And does somebody from the chat mind checking if you can see my submissions? Sometimes there's a little bit of edge case stuff if you're a manager of the chat. What Vim plugin are you using to hide the template? I'm just using the default Vim ability to fold stuff. So I don't really use it much, but I think if you like set the fold method to syntax, then you can. Maybe I did that wrong, but basically you can make folds. It's kind of like collapsing and expanding a tree of stuff. Okay. So there I had a space. Is that what I did? Yeah, so now it'll fold like, way too much. It's folding this if statement, which I don't want. Cool. But that's that's the manual folding method, I think. Yeah, exactly. So I think my template or Vim has custom folding and it folds the template. Cool. All right, let's do the next problem. So generally when you're doing like these kinds of constructive problems and you want to do something with primes and composites, you want to try to find something simpler to do. Like in this case, we're just looking at even numbers. Yeah, I think it's fold method marker, though actually this Vim stuff was not written by me. Mostly written by Socket, who I've tagged in the chat. All right. So let's look at B. So for B, we're given a multiset of n integers. We want to select exactly k of them in a way that the difference between any pair is divisible by m, or I guess print no. Delimiters just means something that you use to mark the endpoints or as a separator. Like a comma is a delimiter in like most programming languages. Parentheses are delimiters. Cool. So for B, the trick to this one is you want to think about, generally when you're thinking about divisibility or things like that, it's helpful to think about modular arithmetic. So if we consider all the numbers, I guess to be more precise, the condition, I guess here they're using m, so I'll just stick with that. M divides a minus b is actually exactly equivalent to a is congruent to B mod M. And this is actually, depending on how you look at it, I think almost by definition. Like this is either the definition of modular arithmetic or the definition of divisibility, depending on what you want to start with. So what this is saying is that, so what this statement implies is that if you have a bunch of numbers that are all equal mod M, then the difference of any pair of them will be divisible by M, which is exactly what the question is asking. So you can rephrase this question as, I should make these boxes bigger. Cool. Rephrase question. Can you select k numbers that are equal mod M? And that's basically all you want to do for this problem. So if we look at one of their examples that they have here, they have, in the example, they have M equals, maybe I can make this a little bigger. Let me know, by the way, if anything is hard to read or could be bigger or smaller or rearranged, because that's a little hard for me to tell from this end because I just see it here on my monitor. Yeah, so in the first example, M equals 3, and your set is 1, 8, 4. So what we want to do here is we want to consider what all of these are mod 3. So you get 1, 2, and 1. And then these two are the same mod 3. So you end up printing them and you print 1 and 4. So cool. Let's code this up. I'll make the coding window smaller. Yeah, that might be good. So here, let's find the frequency of each remainder or each equivalent class mod M, and we're going to take the biggest one and then see if it's more than k or greater than or equal to k. And if it is, then we're going to print that one. If it's not, then we're going to print no. And as a general practice, I like to do this so I don't have any worry about typos or anything like that later in my code. So we want to take this mod M, add to it, and then oh, I guess I can't use key. So I'll use remainder and count. So we're going to loop through this map, and if count is greater than or equal to k, then we're going to print yes, and then we're going to quit, and then otherwise we're going to print no. I guess before we actually do the busy work of printing the things, let's check if I did this right. Oh, whoops, I'm looping through A. I want to loop through the frequency map. Cool. So yeah, this correctly prints yes or no. So now I guess what we can do is we're only going to print the things that are in the bucket that we're looking for. So This is a little bit weirdly written, but I think it should be fine. Basically what we're doing is... All right, this is not right. I printed the wrong number of things. Wait. Oh, right. Okay, I don't want to go through... I want to go through k things. This is a little weird because we're destroying... Yeah, I actually won't even write it like this. I'll just say if size answer equals k, which means we have enough things. That's a much more clear way to write this. Cool. This actually exactly matches the samples, which it doesn't have to. Cool. All right. Let's look at C. So I've actually done C before, but it's definitely a bit of a complex looking problem. It's kind of a long one too. Could not view this contest in gym. What kind of link are you clicking? So if you click this link, it should invite you to the gym. And then clicking this link should get you to the current problem, which I haven't been updating. So let me do that. Let me know if you still have issues seeing the problem. Yeah, I might link to all the original problem sources in the YouTube video instead of to the gym, just in case people want to view it without being logged into Codeforces. I kind of wish you could just make mashups public more easily, but unfortunately you can't. Yeah, so let me know if that works. Awesome. Cool. Let me check that. Qualified 9898 says hello. Yeah, hello. Cool. All right, let's read this problem. So we have this matrix. They've given you an example, 2, 9, 7, 4, 144. It's a pretty big number, 84. And they're telling you to find the GCD of every row and of every column. So the GCD of the first row is going to be 1. The GCD of the second row is going to be 4. The GCD of the first column is 2, then 9, then 7. And then they're asking you to confirm that all 5 of these things are separate. No 2 are equal, and that means the matrix is diverse. And what they're asking you to do, and the magnitude is the largest one, so that would be 9. So they're asking you, given a size of the matrix, you want to find a diverse matrix that minimizes the magnitude. And if there are multiple solutions, you can print any of them. So let's try to make some observations. I'll put them over here. So as the first observation, I'll make a box here. When I click the link, it says the requested URL. All right, so this is kind of annoying, but I think you have to click the contest link while logged in and then click the problem link. Maybe I should link to just the original problems. I don't know. I guess most people watching probably have a Codeforces account, if not all. I'm logged in when I click the contest. Did you click the invitation link first? How? Oh, weird. Did I type the wrong link? Oh, whoops. Okay, apparently my links were just invalid. Oh, I'm missing the /problem. Got it. Uh, okay, cool. So hopefully Neil will fix this link for me. And yeah, how so 2's link should work. All right, so let's see. So if our matrix contains 1, then we can't use 1 anywhere. So for example, we can't use 1 anywhere because if we had a 1 somewhere in the matrix, it would look like, and this GCD would be 1, and this GCD would be 1, which is a contradiction. Oh. All right, let me fix this. Oh, it looks like you do have access. Okay, cool. I set the bot to whisper the confirmation. Okay, cool. So yeah, so here we can't use 1 anywhere. Then what are some other observations we can make? All right, so let's try using a 2. So if we use a 2, I guess without loss of generality, I guess let's just say that, well, it's not quite without loss of generality because we don't know what R and C are, but let's just assume that the GCD of the first row is some value 2. So that would mean that everything here is going to be a multiple of 2. So actually, let's think about this another way. So let's say the GCD of a row is let's say the GCD of a single row is X and the GCD of a column is Y. Then this cell, let's say it has a V in it, then we know that X divides V and Y divides V by definition of GCD. So that means that the product of x and y divides v as well. So where can we go from here? By the way, just as a general note, in the chat, if you have any questions about something I've said or something's unclear, definitely shout it out so I can clarify. Yeah. And cool, I see some familiar names in the chat from, I guess, yesterday's stream who mentioned wanting to join today's stream. So happy to see you guys, like Super MZ. So yeah, so we have x and y. So v could be socket knot. Thanks for the follow. Hmm. Well, I guess let's put it this way. So v could be actually equal to x times y, and or it could be equal to 2xy or 3xy or any multiple of xy. So we would need another element. So we would need some other elements of this column to not be divisible by x. If all of them were divisible by x, then actually, is that even a problem? Oh, well, okay. So actually, here's an idea. If we look at the so if we look at these samples, right, we can see the magnitude of the first sample ends up being 4. Since the GCDs have to be distinct and at least 1. So let's actually see. Maybe that is just always the answer. So let's try for 6. Let's see if we can make the GCDs, or let's see if we can make the magnitude equal to 5, which I guess would be the smallest possible magnitude of, these 5 distinct pairwise distinct GCDs. So let's just say the GCD of the first row is 1, the second one is 2. So then here everything we would have one odd number, and here we'd have all even numbers. Another way to think about this is, so if we do this, and I think I actually vaguely remember this being like doing this problem or a similar one. But let's try filling in the products of all this stuff, kind of like multiplication table style, and using this observation. So this would just be the minimum possible value of each cell if these were the GCDs of the rows and columns. And then are those actually the GCDs? So yeah, so in this case they would be. Maybe I should go to the next page so I have some space. So all right, so here's our conjecture. Our our conjecture is that you have your matrix, you can put 1, 2, 3, 4, and then like 5, 6, 7. And then we would fill each thing out with the product of the row GCD and the column GCD. So let's confirm that these actually are the GCDs. So in order for something to be a GCD, it has to be a divisor, and it has to be the largest possible divisor. So it's clear from this that from the way that we are generating these numbers, it's clear that you would get the divisor because, for example, let's call these numbers Ri and these Ci. So let's just consider C1, for example. The values, I guess actually, these should be the Ci. Oh, CS Practice Live, thanks for following. And these would be the Ri. So if we look at the values in C1, let's say, they're going to be C1 times R1. Whoops. It's actually nice being able to erase. I'm used to working on paper where I do have to scribble things out. So C1 times R1, R2, and R3. And we want to find the GCD of these things. So if you want to find the GCD of a set, you can divide out a common divisor. So for example, if you have the set A, B, C, D, and you know they're all divisible by, let's say, 3, then you can find the GCD of A over 3, B over 3, C over 3, D over 3, and then multiply by 3. So in this case, the GCD would be C1 or Ci, let's just make it a little more general, times the GCD of all these row values. And if we assign the row values this way, so that they're consecutive, then the GCD of any two consecutive numbers is always 1. So this GCD would be Ci, which is what we want. So this assignment would always work. The only issue would be if we don't have two consecutive numbers to make the GCD 1, in which case that would either mean that R is equal to 1 or C is equal to 1 in the problem statement. So let's consider R equals 1. All right, well, first let's consider both equal to 1. Then we can just print the matrix 1, and the GCD of the rows and columns would, or whatever value we make it, the GCDs of the rows and columns would be the same, which means it's impossible. And now let's try R equals 1, C greater than 1. You gotta print D and, oh yeah. Cool, Eknerwala is on the ball. So if R is 1 and C is greater than 1, or vice versa, you basically have a single row of values. Let's call them x1, x2, x3, and so on. And the GCD of all of them together, let's see. So the GCDs of the rows would just be the values themselves. And the GCDs of the... All right, nice. I got my first spammer. That's pretty cool. Does anyone want to ban them? I don't know. I don't actually know how, but if there's a mod in the chat, maybe I can do this. Nice. That's actually a great point. This is wrong. For example, if 4 divides 12 and 6 divides 12, it's not the case that 24 divides 12. So I guess wrong reasoning, but right So this is actually true, I think. The LCM of x and y would divide v. Yeah, so so great point. X crush X crush z. I think, yeah, I think this is true. Now that I replace this with the LCM. Oh, whoops! I wasn't actually displaying what I did. But yeah, here's the example. LCM 4, 6, and 12. Yeah, so in this case, if you have just like a one-dimensional matrix almost, you could, the GCD of all these numbers, if we made them consecutive, would be 1. And the GCDs up here would be x1, x2, dot, dot, dot. So we can make the numbers 2 through, I guess, n plus 1. And then the magnitude would still be minimized. Cool. So I think this works. Pretty sure from what we discussed. So let's try coding it up, and we can move on to D. um, so print 0 if there's no solution. And then otherwise, R rows. Okay, cool. So let's just make a vector for the row GCDs and for the call GCDs. And we want to start by, so we can just assign the numbers from 1 through n, where n is r plus c. The only problem is if we, so actually I can start with them empty. The only problem is that if one of these is equal to 1, we want to make sure that's the one that contains the single 1 in it. So I guess let's start by assigning the numbers to r first, and then we'll have this special case if c equals 1. Else we want to do so we're basically setting up our rows and our columns. And let's iterate over the columns. So here we're just going to go through every cell of our final array. Cool. All right, let's look at these samples. So here we have 3 and 4, the GCD is 1. 6 and 8, the GCD is 2. 3, 6, GCD is 3. 4, 8, GCD is 4. So that's exactly as we expect. And then let's just test this where we have one of them being 1, and then the other one being 1. And we get this, which is correct. Cool. Yeah, it's always good to check your edge cases, especially for problems like this where it's a constructive with some casework. Um, Cool. And definitely let me know if the pace is, could be faster or could be slower and more detailed. If it could be slower, definitely let me know what part is missing, because I think that would definitely help me to make this as useful as possible. Is my internet down? I guess it's not, but Codeforce is a little slow. By the way, let's see how people did on this contest. So it seems like we're getting to the point where the problem solves start to become a little more scattered. I see a couple people actually solved everything or almost everything, and a few people have virtualed it, which is awesome. Always nice to try to practice under some time pressure, though um, it's definitely more nerve-wracking. Okay, cool. All right, so let's look at D. It's a little longer. Cool. So actually I remember this problem. I thought it was quite a nice problem. So here somebody wants to paint, this is a bit of a combinatorics problem. They want to paint the tiles in different colors. And they have this condition where a path will be aesthetic if any different tiles where j minus I is a divisor of n, other than 1, of course, they have the same color. And then here they have a more mathematical description, which is nice. It's a little less ambiguous, easier to understand. And what's the maximum? Oh, so that actually is not a combinatorics problem. This is just the maximum number of colors you can use, as opposed to how many colorings are there or something like that. Cool. So let's look at these samples. Cool. Yeah, so now we're working on D. So cool. So let's look at the example where they have n equals 5 first. So we want to see if I minus j is a divisor of n greater than 1. So let's list the divisors of 5 that are greater than 1. All right, so there's only 5, which means that if two tiles are 5 apart, they have to be the same color, which isn't a restriction at all, which is why the answer is 5. And then for their example with n equals 4, which is a little bit more complex, the divisors are 2 and 4. We don't even really need to consider 4, because as we saw with 5, that would match a tile to a tile that's not in the grid at all. So in this example, we have 2. And then as we saw, you can kind of color almost greedily, where you color like this. So anything that's 2 apart would be the same. So we're kind of dividing the sequence into like periodic parts that are all that distance apart. Cool. So let's just try, another example, n equals 6. So here the divisors are 2 and 3. And this is pretty interesting because 2 and 3 are only 1 apart. So this should kind of remind you, well, not necessarily should, but this reminds you a little bit of, I think it's called Bezout's identity, not sure to pronounce it, but basically you can imagine this. If you have 1, actually I'll zero index things. If you have 0, then that's going to be the same as 3, because you can add 3. And then that's going to be the same as 1, because you can subtract 2. And you can continue this process going to 4, and then 2, and then 5, and then 3. Hopefully I added that right. But if you continue this process, you get that the answer is 1, because all the tiles have to be equal in this example. So yeah, so if you have 2 divisors that are 1 apart, then the answer is going to be that everything's the same color. Cool. Two new followers, Dame Monketo and Marin03, or MeIron03. Howso2 asks, wait, why? Great question. So what are you asking why to? Let me know exactly which claim was confusing, and I'll try to clarify that one. Meanwhile, I'll add a little annotations. Right. While I wait for the question, what's the... Oh, can I write that? That's actually a great idea. Okay, I'll zoom this in. So it's called Bezout's identity, or Bezout's lemma, however that's pronounced. And let's see if they have an example. Okay, cool. So here they have an example. If you have 12 and 42, their GCD is 6, and it's possible to, I guess they don't actually have a clear example here, but anyway, you can take 42 minus 36 and get 6. This is basically kind of the same reason why the Euclidean algorithm works to find you a GCD. You can kind of subtract, if you take the bigger number and then you subtract the smaller number a bunch of times, and then you take the smaller number and you subtract that remainder a bunch of times, and so on, you get to the GCD. So this is basically a property of the, this is kind of a consequence of the Euclidean algorithm, I think, is the simplest way to understand it. Yeah, so the one thing there is that relies on being able to add and subtract things to an arbitrary amount, because, and that might actually take you past the boundary of this path, in which case it wouldn't actually imply. So this seems like it's implying that if you have 2 divisors with a GCD of 1, then you can get that all the tiles have to be the same. But let's try to prove that in a little bit more detail. So let's say you have A and B divisors, GCD AB equals 1. And let's just say A is less than B for concreteness. Or maybe we don't want to do that yet. So now, by this identity, we can find there exists SY, X and Y, such that AX plus BY equals 1. So this would kind of be like we want to take like some hops forward and then some hops backward so that the net distance here is 1. And that would show that all the tiles are the same color. So then one of these has to be positive and one of them has to be negative, these being x and y. So let's assume x is greater than 0, y is less than 0. So what we can do is we can follow the following algorithm. We can always add a as much as possible until it's possible to subtract b and then subtract b. So you would get something like this, where you take some forward hops and some backward hops. And let's try to show that this is always possible to do without spilling over the end. Yeah, this is the, yes. Yeah, the thing that Neil described in the chat is the same identity that we were going over a minute ago. So that's the link if you want to read more on your own. So since a and b both have to be divisors of n, they have to be so I guess what we want to show here is that you can always either add a or subtract b from your current point. And the reason that that's true is that a has to be less than or equal to n over 2, and b has to be less than or equal to n over 2, and they can't be equal. So that means that a plus b is less than n. So I think that implies that you can always make at least one of the steps towards your target of 1. And then without either hitting a negative number or hitting a number that's past n, or I guess equal to n if you're 0 indexing. Um, okay, cool. All right, so let's try. One second, actually. I'll be right back. Cool. All right, I'm back. Sorry about that. I'll set it back. Cool. I think my audio is still working. Okay, cool. So where were we? So we were at this point where oh, and as a quick note, if all the divisors of n have some GCD that's greater than 1, um, it's clear from that that you can't. That only shows that things that you can only move by a multiple of that in your steps, and then you can divide that out from all the numbers. So you can basically show that it's the same as if you had 1 as the GCD, but then multiplied the answer by that other. That was a little unclear. If all numbers have GCD equal to G greater than 1, then we can divide G out from them. Cool. Thanks, Hauso, and thanks, Mayank, for checking in. So cool. So now what we want to do is we want to figure out how to figure out the GCD of all these divisors. I guess one thing that we could do. Oh, Mayank, thanks for the follow. And one thing that we could do that would be relatively simple is n goes up to 10 to the 12th, so we could just find all of the divisors and then find their GCD and then output that. Another thing to note is that the GCD of 2 primes is always 1, as long as they're distinct primes. So if our number n has multiple prime factors that are different, then we know the GCD would be 1, and then you can only paint it in one color. And if it has only one prime factor, that means that it's either a prime itself or it's a prime power. For example, 3 cubed has divisors 3, 9, 27. So that's another thing that we can check. But I guess let's implement it, I think, the way that's slightly simpler, which is to find all the divisors and then find their GCD. So let's find the divisors. So let's initialize the answer to 0. And then, oops, I'll use longs. Whoops, I guess we can initialize this to n instead of 0. Cool. All right, cool. So let's try to analyze this a little bit in case people aren't familiar with this method of finding divisors. So if you want to find all the divisors of a number, you only have to check numbers up to the square root. because for any divisor, either d or n over d is going to be less than or equal to the square root. One will be smaller than the square root and one will be bigger than the square root. So this allows you to check all the divisors in square root n time, which is, in this case, square root of 10 to the 12th, which is 10 to the 6th. And and then you can find the GCD, which takes, I guess, log n time. Though actually, if you have to find the GCD, I've seen this fact a lot recently. If you have to find the GCD of a bunch of numbers, it's actually faster than you might expect because of the way the Euclidean algorithm works. But anyway, this should work. Let's try submitting it. I guess we can test on a few more examples first. So for 6, we get 1. For 27, we get 3, as we expected. For 30, we should get 1. And then I guess, yeah. I guess pacing-wise, we've got through 4 problems in about an hour. So, the problems will definitely get harder from here on out, but I'll try to keep it efficient. um, cool. Is the intuition that if you have yeah, so how so? That's exactly right. The idea here is that if you have 2 coprime divisors, you can always move to the right 1 square with some combination of hops. I guess I actually didn't completely prove that here because I just showed that you can get from 0 to 1, but I didn't show that you can get from 1 to 2 and 2 to 3 and so on. Well, whatever the smallest divisor is, you just need to get everything up to that, because after that you can go from there over. So I think that should be fine. Yeah, I think the smallest case would then be something like, I kind of wrote this a less than or equal to b less than or over 2, but I think really it's like a is going to be less than or equal to n over 3, b is going to be less than or equal to n over 2, and then their GCD is going to be less than or equal to. Where is your GCD function? I can't see it in your template. So I actually don't have a GCD function. This is standard GCD. How did you solve the boundary issue again? So actually, I think I explained this missing a couple of details. I did not fully explain the boundary issue problem. So let's try to, I want to start programming, but how do you incorporate math into coding? Also, why would you incorporate math into coding? Well, in this case, we're discussing like competitive programming problems, like the ones linked if you type !link. And a lot of them involve a lot of math, just because it makes the problems more varied, more fun, more interesting. All right, so let's try to think about how we can go all the way through this without hopping completely outside. So let's say A, B, are two smallest prime divisors of n. As an example, you could have 3 comma 5. And that would make n 15 or 30 or something. So what we want to do here is show that we can get from 0 to 1 and from 1 to 2. And then that would actually be good enough if we can get from 0 to 1 to 2, because we also know that we can get from 0 to 3 and from 3 to 6 and so on. And then we also know that we can get from 1 to 4. So we want to show that we can always get from, I guess, from 1 to 2 is what we would want to show. So we want to show that we can get from a minus 2 to a minus 1. And let's say your numbers are in 0, n like this. So we know that a is less than or equal to n over 3. And what else? Well, if we're still at something that's less than a, we can always add either a or b. Yeah. Oh, yeah, actually, how so too? That's a much nicer solution than what I'm thinking. Um, Wait, actually, is that um the same or different? Okay, right. So here's what we want to do. Let's consider multiples of a modulo b. Right, so if you have two colors, you're right that this will definitely only connect to the two. But I think the same idea works for anything. So we know that anything that has the same remainder mod b has to be equal. And we know that all multiples of a have to be equal. So if we consider a, 2a, 3a, etc., up, I guess we can start with 0, and then we can go up to b minus 1a. These would be the multiples of a that are definitely less than n, because we know that n is greater than or equal to ab. And these are b multiples of a. And because A and B are coprime, we actually know that if you take the numbers 0 to B minus 1, and you multiply all of them by A, I'll write it like this. That just forms a permutation of the original B minus 1 things. Meaning that you have one element that's congruent to each residue or each remainder mod B, which actually is a pretty nice way of showing the claim. It's relatively clean compared to what I was doing with the hops, for sure. And you can see that this is a permutation because you can divide by any number that's coprime to your modulus. And if you can do that, then that shows that this function of multiplying by A has to be invertible, which means that it has to permute the values since you're going from an equal size set to another equal size set. Cool. So that's actually the proof here for D. All right, let's check out E. Orac and LCM. I will set the link. Cool. So we want to define the GCD and the LCM. All right, these are the standard definitions. And they're saying that they have a sequence A with length n, and you want to find the multiset. Okay, so you want to consider every pair of elements, find their LCM, and then find the GCD of all the LCMs. So they have an example here. You have 10, 24, 40, and 80. And if you take all of those pairs, these are the LCMs, and their GCD is 40. Apparently, it's not hard to see. Cool. All right, so let's think about this. A pretty standard technique that's helpful when you're thinking about divisibility or divisors or anything like that, GCDs, LCMs, is to think about every prime separately or think about the prime factorizations. So first, what we want to do is, so every number has a unique factorization as the product of some primes to some powers. So if we can just pick one of those primes and find its power in the answer, then we could do that for all the primes and solve the problem. So let's, oops. So let's just find the power of P that's going to be in this answer. So let's go through an example. Let's find the power of, let's say, 2 that's going to be in the answer for this. So let's say P equals 2, and then A equals 10, 24, 40, 80. So now let's look at how many 2's are in each of these things. So then you get, well, I'll write how many there are instead of the power of 2. So you have 1. Actually, maybe it's a little more clear if I just write the power itself. So this is 2, this is 8. This is 8. and this is 16. And so now it's saying you want to find the LCM of every pair. And if you're looking at only prime powers of the same prime, the LCM equals the max, and the GCD equals the min. And the reason for that is that any two numbers definitely divide each other. Like any two powers of 2, one of them divides the other, unless they're equal, in which case they both divide each other. So the smaller one is going to be the GCD, and the larger one is going to be the LCM. So now what we're doing is we're finding the max of every pair, and then we're finding the min of all of those. So here it's pretty simple to find the minimum of all the maximums of all the pairs, because it's pretty obvious just from inspection that this is the pair that's going to give you the smallest maximum, which is 8. And then if we try p equals 5 for the same example array, we get 5, 1, 5, 5. And this is a valid pair that gives you the smallest maximum, which is 5. So the answer is 5 times 8, which is 40. So this immediately gives us a solution where we could prime factorize every single number, and then we could go ahead and compute the power of every prime in our answer, and then multiply those all back together to get the actual answer. And let's actually see count primes less than. We'll try Wolfram alpha. Whoops. So there are 17,000 primes, so this would actually be too slow if we did it this way. However, I think this does kind of lead us to an answer, which is so we want to find some process that we can do that's equivalent to taking the minimum, like if you consider only how it affects a single prime power, we want it to be equivalent to taking this minimum of the maximums of the pairs procedure. So if we're taking the minimum of the maximum of the pairs, this basically means we're finding the second smallest number. So, or equivalently, we're considering removing each number and finding the min of the remaining stuff. So consider removing each number and find GCD of remaining array. So let's actually test this out with one of these examples. Or with, we can, well, I don't want to test the last example because it's kind of long, but let's test this example. So if you remove 10, the GCD of 24, 40, and 80 would be 8. Wait a second. Is it right? Second thread says, good morning. Definitely to all my Indian viewers for whom it actually is, I think, pretty early in the morning. So Thanks, second thread. Yeah, so if we remove 24, the GCD of the remaining stuff is 10. Wait, did I get mixed up here a little? Ah, right, okay. So for each prime, we want to separately figure out what we get the biggest stuff from. So let's keep doing this. I guess first I'll go through the individual prime arrays, and I'll use a different color. So if we remove 2, the GCD of the remaining stuff here is 8. If we remove 8, it's 2, and then for all of these it's 2, because you still have this 2 here, kind of ruining things. And then here, if you remove 5, the GCD is 1. Here it's 5, and then here it's 1, and here it's 1. Cool, second thread, thanks for the follow. Hope to catch you in future streams. Yeah, and if you... I'll erase these so I can write them more clearly here. If you remove 40, then the GCD of the remaining stuff is actually just 2. And if you remove 80, the GCD of the remaining stuff is just 2. So these candidate answers up here actually kind of encode the, if you look at these columns, these kind of multiply together to get you your results. So if you wanted to be able to take the max for each separate prime, you could take the LCM of these values that I've circled in blue. And that would actually be just the answer to the problem. So let's try implementing that. I'll put that there so it's pretty big. Oh no, I'll move it up a little bit. So I can see my terminal. Cool. So what we want to do here, so there's one last problem with this, which is that the algorithm that I described here would actually be quadratic time, because removing each element would give you, to check the GCD of all the remaining elements, you would have to loop through them all, and that would take linear time, and then you're doing a linear number of those candidates. But we can actually solve this by pre-computing prefix GCDs and suffix GCDs. Cool, and I'll just make a LCM method. Actually, is that already there? Oh, it is. Okay, awesome. So I don't even need to do that. So vi prefix. Let's see. For int x colon a. Wait, what? I thought I had this in my template. Hmm. Actually, a little curious what this build error is. It's not completely necessary to actually debug, but I'll take a quick look. Maybe there are some C++ experts. Um, hmm. I could have sworn this worked before, like when I first wrote it. All right. Okay. This is, I guess, not necessary. um, it's a little annoying. Problem K for the number theory set. Which one is K? Ah, yes, product-oriented recurrence. All right, a small spoiler for K, but second thread is in fact on the right chat or on the right track here. It is a matrix exponentiation problem. Um, I think this was an example of a problem that was easier than the setter thought it was going to be because the editorial had a really cool trick for it, but you could just solve it without that trick pretty easily as well. Right. For So we want to find the LCM of all these GCDs. So here I is going to be the element that we remove. So the count of things on the left is just going to be I, and the count of things on the right is going to be n minus 1 minus I. And then our candidate is going to be the LCM, or no, the GCD of prefix left, suffix right. And then we're going to do answer equals the LCM of, here, I'll actually just copy this. Yeah, great call. I have a typo here. This should be suffix dot back. Ah, okay, cool. I got every sample wrong because I didn't print anything. Pretty common mistake. Um, oh, and I want this to start with 0 isn't a valid starting LCM, so I'll just start this as the... Oh, I can just start this as 1. Okay, cool. That's the identity for LCM. Cool. So hopefully this explanation made sense. The kind of key idea here is that if you consider every prime separately, you can try to find a process that will get you the correct answer for every prime power, dividing the answer and dividing the numbers AI. And then this kind of allows you to solve it for all the primes in parallel, which is kind of the same as just, solving it normally. um, Wrong answer. So I want to find the... Let me check to make sure I actually understood this correctly. Okay. So I think the problem here, let's see. Let's try adding a test case. I'm just going to try here having everything be a multiple of 2. And let's try running it on that test case. It's kind of slow. Weird. Okay. So this prints 2. But if we actually look at it, every pair definitely gives you something that's at least divisible by 4, since every pair is divisible by 2. So I think the error in reasoning here is that... Wait a second. Never mind. Right, because we're not actually finding the products, we're finding the LCMs. LCM, yeah, okay. So is the correct answer here actually... The correct answer here actually is 2, right? LCM of 2 comma 6 is 6. LCM of 2 comma 4 is 4. Their GCD is... I wonder if I have a bug or if I just wrote something weird. Can you show your code again? Yeah, I might just have like a bug in how I wrote this. Oh, I forgot to reverse suffix. Oh wait, no, I don't want to reverse suffix. Could it possibly just be an overflow issue? Like I should have been using longs. Let's see. So yeah, so the LCM of 2 pairs here could be up to this number squared, which would overflow a 32-bit int. If you took like this number and like this number minus 1, their LCM would just be their product because they're coprime. So that would cause an overflow issue. So let's try resubmitting now. Also kind of makes sense, right? Because it's wrong answer on like, a few tests in. All right, yeah. So always watch out for overflow. um, Definitely good to think about whether you want to use 32-bit or 64-bit for every problem. All right. Problem F, meaningless operations. Yeah, we got some nices in the chat. I'm sure people in the chat know that feeling, right? Where you just have overflow. um, can GCD and bitwise operations have anything in common? Guessing the answer is yes. I love Totoro. Thanks for the follow. Nice. We're at 183 followers. I wonder if I should do any big follower goals sometime, like at some nice round number, like 200 or 256. Okay. So here we're given an integer a, and we want to find an integer b that's less than it. And then we want to find a XOR b and a and b, and then find their GCD. Definitely a bit complicated sounding. So let's try to think about what this means in terms of bitwise operations. Oh, okay, and then we have to do it for 1,000 numbers that I guess are all separate. And the numbers could be up to 2 to the 25th. And they have some examples here. Cool. So let's just pick an example. Let's say a equals 5, which is 1, 0, 1. So we want to pick some b that's less than a, and then we want to do a and b and a XOR b. And we want their GCD to be maximal. And for this example, they're actually saying that the answer is 7, which is actually larger than both the input values, which is pretty cool. So their example was if you do b equals 0, 1, 0, their and is 0, and their XOR is all ones. And we have this nice fact about GCD, which states that this is, whoops, that states that this is true. And the GCD of a number is always less than or equal to the number. Yeah, I agree. This is a bit of a silly problem from what I can see so far. So it seems like what we probably want to do is see if we can make all the bits in one of them 0 and all the bits in the other one equal to 1. Which is not always possible. So in order to make all the bits equal to 1, we want to take something that's a bunch of 1s, and then we want to XOR that with A and set that equal to B. And then A XOR B would be equal to A XOR A XOR a bunch of 1s, which would be equal to a bunch of 1s. And then A and B would, I guess, always be equal to, wait, would that be equal to 0? Yeah, so that would always be equal to 0 because 0 and 1 equals 1 and 0 equals 0. So for every bit, you're going to have 1 0 and 1 1. Time to bust out the hard-coded 25 answers. Yeah, all right, so this is a type racer problem. Oh, but I do have to somehow figure out how to map these to them. So I'd have to do 2 to the 25 hard-coded things, which is too much for me to type on this stream. But yeah, so I think what we want to do here is basically find the largest bit string, which would be all ones, that has the same length as A. Let me, oh, my computer's slowing down a little. Where x is 1 less than a power of 2. So if A is already all ones, then... Oh yeah, so B can't be equal to 0. But in my example, I'll go back to the Jamboard. So there's a special edge case. If A equals a bunch of ones already, then B can't be equal to exactly 0. So we can't actually do this. So let's see. Actually, conveniently, they have one of those in the in the samples. So here we have 3, which is 2 ones. So I guess let's see. So if A is all ones, then A XOR B is kind of like not B. Or I guess to put it more mathematically, it's going to be A minus B. And then A and B is going to be equal to B. So in that case, our answer will be the GCD of B and A minus B. So do I need math knowledge? Yeah, so it depends if you have math knowledge or not. As Second Thread said, it's good to have to be pretty well rounded. For example, if you were amazing at number theory and terrible at tree problems, you might be able to solve like problem F if it's a number theory problem, but you wouldn't be able to solve problem C if it's a tree problem. And as for what topics, I think the most efficient thing to do is to just start with solving a lot of problems. Yeah, just solve a lot of problems, and as you run into topics that you're not good at or you're not familiar with, then learn those topics. And that'll kind of automatically make sure that you're learning the topics that show up the most in problems at the level that you are trying to solve. As opposed to, spending a ton of time like learning some fancy topic that won't actually show up in any problems you can solve. For example, if there's some, yeah, so basically, if that's your goal, then you want to try to solve a bunch of A's and B's and probably C's. Just see what topics show up on those and learn stuff as you need it. Mark6Mark, thanks for the follow. Yeah, there's definitely no point in like seeking out topics excessively because the main thing you want to focus on is just improving your problem solving skills in general. But I would say for math in particular, it's definitely nice to have a pretty decent math background because I think having a broad math background helps you make a lot of connections between different things and understand things pretty readily. Even if it's not strictly necessary, it definitely helps. All right, so back to this. So we want to find GCD of A minus B and B. And this is actually equal to GCD of A, B. So yes, everybody should be a math major. Yeah, for sure. And thanks CodeMonkey JS for following. Glad my advice was worth it. So I guess for that example, um, as second thread pointed out, there's a special case. And I think what you would want to do then is just make make B equal to the greatest divisor of A that you can. And then their GCD would be the answer. And the GCD of A and one of its divisors is just the divisor. So let's kind of squeeze this in here. Let's say A equals, what's 1 less than a power of 2? 15. Then B could be equal to 5. And then you would have 1, 1, 1, 1, and 1, 0, 1, and then say, yeah, so you had 5 and 10, and the GCD would be 5. Cool. All right. So let's there's some weird issue with MacVim. All right, cool. So oh, that's the 25 cases that you were saying to hard code. Okay, that makes more sense. I thought you were saying to um I thought you were saying to hard code all 25 possible lengths. Um okay, cool. So int a read a if how do you find the number of bits in C++? Pop count? Built-in pop count, I see. So this will tell us if A is all ones, kind of like we discussed as the edge case. Then for int I equals 1. And we'll go through all the divisors like this again. And we don't want to go through exactly A. Yeah, because it has to be less than A minus 1. So and we actually don't even need to do the max with D like we normally would because we want the bigger divisor if you have a pair. Print answer, return. What's the definition of fancy plus and and? So this is the bitwise XOR operation, and this is the bitwise AND operation. I'll quickly review what they are. So with XOR, what you're doing is if you have two different things, you end up with a 1, and if you have the same thing twice, you end up with a 0. And then for AND, you only have a 1 if both things are 1 to begin with. Yeah, fancy plus. Cool. By the way, second thread, I'm curious. I mean, obviously you're not bad at math in an absolute sense because you're so good at Codeforces, but do you consider like more mathy stuff to be one of your like weaker areas? I like recursion. Right now we're doing F. We're just wrapping up F from the mashup, and then we're going to move on to G, of course. So how do I find the largest? right, we'll do this all right, so here we're gonna round a up to the next thing that's that's 1 less than a power of 2. Let's see if that actually works. There's definitely a much nicer way to do it. I think using like built-in CLZ or something. I guess I'll try to do it that way too. So this counts the leading zeros of A. And then to find the trailing, I think this will work. No, that did not work at all. I guess I'll do this, which is kind of gross, but basically the idea is you So this should give you 3. Okay, so that works. So why doesn't this work? There's 30 leading 0. Oh, I see. Okay, yeah. So I want to make this as many ones as possible. Oh, I guess I would do -1. No. Ah, okay. All right, so let's not do that. I think this is the better way to do it. 31 minus CLZ. So this is where I really miss Java. They have in Java I would just do something like this. I feel like this highest 1 bit or whatever they call it is way easier to understand than built-in CLZ and then this magic number 31. All right, let's see if this works. And yeah, it's probably something with the, oh, whoops. So I want to, I guess, do it by 1 more, and then I want to subtract 1. Okay, so personally in this case, oh, actually, I would get time limit exceeded if I did it with my while loop, because we have to do 1,000 cases. I forgot about that. Cool. All right, so let's submit this. A lot of times in ICPC, there'll be some mathemagic problem. Yeah, so I guess I'm probably, well, I mean, I guess now I do a lot of competitive programming, but back in high school, I mostly did like math competitions and some physics competitions and like a bit of programming competitions on the side of that stuff. So I have a bit more of a, for me, I like the mathy problems a little bit more. Since, I kind of enjoy and miss doing math, but, um, people don't really do math competitions when you're like an adult, but you still can do programming competitions, which are basically math competitions with extra steps. All right. So let's do G. All right. So Hilbert's Hotel. So what we're doing here is we have one room for every integer, including positive, negative, and 0. So all integers, plus or minus, whatever. And what we're doing next is we're finding k mod n for each integer. That's just the remainder modulo n. And then what we're doing is we're going from k to k plus a k mod n. Yeah, that makes sense. So let's consider all these numbers. Isn't the solution for the last problem? Yeah, so mark 6 mark. I guess I'll look at that real quick. So that is what we got for all the cases where, yeah, okay. So you're on the right track. There is an edge case where if A is already all ones, then you can't actually do that. Oh, what is this? Mark 6 mark. Yeah, if people feel free to link your Codeforces profiles so we can all follow each other too. But yeah, there's this edge case where we can't make b equal to 0, so then we need b to be the largest divisor of a, other than a itself. So that's the edge case, and then this is the solution that you described. So the edge case is like almost more than the rest of the problem. Yeah, I also like the math part. Okay, so for this problem, let's consider the people in room K and K plus N. So the person in K plus N will go to K plus N plus a K mod N. Oh, whoops. I need to move my whiteboard. So we'll notice here that this K mod N in the subscript of A is going to be the same because adding N doesn't change the value of K mod N. So what this means is any things that are initially apart by a multiple of n will always stay apart by a multiple of n. Oh, Justin PC and Benzene, thanks for the follows. So what this tells us is we're going to have to, okay, and we want the shuffling, basically we want the shuffling to be a bijection. We want everything to get mapped to a unique element. Axbel and Radomain, thanks for the follows. So the way that we want to look at this is we can just consider all the elements from 0 to n minus 1 and make sure that all of them get mapped to something unique. So 0 gets mapped to 0 plus a 0. 1 gets mapped to 1 plus a 1. And n minus 1 gets mapped to n minus 1 plus a n minus 1. And we want all of these numbers to be different. So what this means is, you may notice a pattern here. We can just take ai plus I for each I. Yeah, we want them to be different mod n. Yeah, that's exactly right. If you could also add n to all of them. Wait, actually, do we need a distinct mod n? Yeah, I think we do. Yeah, so you can kind of imagine you're moving all the things that are 0 mod n to be something else mod n, and their offset relative to each other will be constant. But if you map all the stuff that's 0 mod n and all the stuff that's 1 mod n to both be, let's say, 5 mod n, even if you map them to different values, like one gets mapped to 5 and one gets mapped to 5 plus 2n or something, there'll still be a collision between those sets. And this one I actually already coded and submitted just to test out the mashup. So we can just look at that code. Instead of typing it up on stream. So here, yeah, so I find ai plus I, and then I find all of their remainders mod n. And the reason that we mod by n, then add n, then mod by n again, is just because in C++, and I think most other languages, if you have a negative number and you mod by n, you end up getting a negative number as your result. So then you can add n to make it positive and then mod it again. I guess you don't need to add n and mod it again, but in case your number is already positive, then this mod n just cancels out the adding of n. And then we're just checking here to see if all the values are unique using some C++ STL stuff. Stage 3 ghost, thanks for the follow. And then we're just printing yes or no. Great. So let's, all right, same GCDs. All right. Cool. We're getting closer to the end of our problem set, to the tougher problems. Cool. And yeah, feel free to definitely ask any questions if any of the reasoning was unclear or there's any background you'd like me to explain more, or, if I just missed something. Okay. So here we want to find the number of integers x such that GCD of a comma m equals GCD of a plus x comma m, given a and m. Let's see. So let's just go through an example. So in the first example, a equals 4, m equals 9. And so their GCD equals 1. So we want to find other things where the GCD mod 9 is 1. Or sorry, the GCD with 9 is 1. And note that adding or subtracting m, so GCD of a, or yeah, I'll write it like this. if you add or subtract m from the other argument of the GCD, you don't actually change the GCD. Ayush, thanks for the follow. So what this means is if you consider all the values of x from 0 to m minus 1, and then you add a to all of them, you're basically just going through all the values from 0 to m minus 1. So what we want to do is we want to count. So let y equal a plus x for convenience. So we want to count y in 0 to m minus 1 such that GCD of y comma m equals GCD of a comma m, whatever that happens to be. So I think there's a couple ways to do this, but let's just consider whatever the GCD of a comma m is, let's say that it's equal to g. So let's just consider dividing. So then we need y to be a multiple of g. And we already know that m is a multiple of g because g is the GCD of a and m. So we can just divide g out completely. So then we want to find the GCD of, let's let z equal y over g. Then we want to find the GCD of z and m over g equals 1. Right, just GCD of a comma m, which is g divided by g. So this is actually the totient function of m over g, in the sense that this is like exactly the definition of the totient function. I'm pretty sure. Okay, I just want the definition. Okay, yeah, it counts the positive integers up to a given integer m that are relatively prime to n, meaning their GCD is... So here I'm doing from 0 to m minus 1, but I could also do from 1 to m, and it would be the same. Since all that matters is what you have mod m, I believe, for this GCD. Cool. And then for this, we want to calculate the totient. Let's actually see how they suggest calculating it. Oh, let's see. Yeah, so here what we're doing is for each prime that divides n, we're finding, so 1 over p of the numbers dividing n are going to have that prime in common, so they're not valid. And the reason you can multiply these is it turns out that all the primes are independent. Like, you can remove half of the numbers because they're divisible by 2, let's say, and then you can remove a third of the remaining numbers because they're divisible by 3. And I think that's a consequence of the Chinese remainder theorem. So yeah, I guess let's try implementing this this totient function. And we have to do this somewhat efficiently because m goes up to 10 to the 10th, so we can't just iterate over everything. So I think we have to do it this way. So let's see. So here we're dividing out the GCD, and then we never actually have to use a again. And now we want to find the totient of m. So first, let's start with all the numbers. And then what we want to do here is we want to somehow find all the primes that divide m. So let's see what the best way to do that is. So all the primes that divide m have to be less than the square root of m, except for at most one of them. Yeah, because if you multiply, you couldn't have two different primes that are both more than the square root of m, because then their product would already be more than m. So I just had this pre-written civ code thanks to Socket. I don't know if he's still in the chat, but civ. And then the maximum value here we would need would be the square root of m, which is 10 to the fifth. So let's just add 5. I think adding 1 is fine. Cool. So, oh, we can just iterate through all the, we can just iterate through all the primes. So first we'll check if the prime divides it, and then if so, we'll say answer equals we'll do this, and then here we'll divide out the prime. And then finally, we might have one prime left. So if m is greater than 1, then we'll want to do, so I'll do it this way. Cool. Let's try printing this. I think this should work. Maybe I made a mistake implementing Toshin. Cool. All right, let's try submitting this. This is definitely a bit tougher than some of the previous problems. Like knowing that this thing of, we got to the point where we were like, we want to count these things, but knowing that that has a name is pretty helpful for knowing how to implement it. You can just Google how to implement Toshin function. You could probably even Google it and then find an implementation and copy paste it. All right, we're still in the queue. By the way, I was thinking of doing a post-contest stream after tomorrow's @coder beginner contest, or I think tonight, depending on your time zone. So let me know if that's something that you'd be interested in watching, or if it's something you wouldn't be interested in watching. That'll just help me make my decision. All right, cool. So counting arrays. So let's look at this problem. So So what we want to do here is we want to figure out a y factorization of x. And this means that you factor x into y numbers. Oh, and I guess I should link the @coder beginner contest in case people aren't super familiar with when it is. That would be this contest to be precise. Yeah, unfortunately there is Toki right after this, so I wouldn't be able to do that if I was doing the stream, but you know, I'm a content creator now, so I gotta prioritize the content creation over my own competition. Cool. All right, so let's check out this problem. They have some examples here, and here's a little gotcha. You could have negative numbers. Since this just says integers, it doesn't say positive integers. So let's see. So here we want two things that multiply to 4. So the trick to this one is you want to consider, as we kind of mentioned before, if you look at the operations that we're doing here, we're just multiplying numbers. So if you have multiple prime powers that divide a number, it'll end up acting on all of those independently. So what this means is you can consider each prime or each prime power that divides your number, I guess x, separately. So let's say x equals p1 to the k1, p2 to the k2, p3 to the k3, dot, dot, dot. Then, and then let's say we have to find a 3 factorization of x. So you kind of have these 3 buckets that you can say are the 3 numbers, and you have k1 of these p1s that you can distribute however. Like maybe you could do it like this. And then you can also distribute the p2s and so on. So this ends up becoming a combinatorics problem using stars and bars, or I think there are a lot of other words for it. So you can basically imagine you have all your copies of P1, and then you have 2 dividers, and you want to figure out the number of ways to rearrange these. In this case, we would have y equals 3. That's why we have 3 of these blocks and 2 dividers. So the answer would be the product over I of k sub I plus y minus 1. Would I be interested in looking at a leet code problem and explain how I'd approach or solve it? Yeah, I'd definitely be happy to do that. I think at the tail end of this stream, after I finish these number theory problems, I'd be happy to take a look. I do want to kind of focus on the main agenda of this stream, which is I think what people are here to see, which is number theory. If it's number theory related, I'm definitely even more likely to want to solve it. But yeah. And I also have pretty regular, like, just miscellaneous problem solving streams where I don't have a specific thing in mind, and then I'm happy to work on whatever people in chat suggest. So that would also be a really good time to surface this kind of leet code problem. But yeah, for now we have a couple more number theory problems, and then feel free to drop the leet code link in the chat. Cool. So this is kind of a standard counting technique. I'll Google it. Stars and bars. So here, right, you have your stars and your bars, and you want to reorder them somehow. So if you add the total number, that's kind of how many spaces you have to like write a symbol, and you want to pick some number of those symbols to be stars. So I think your answer would be something like this, and then there's a little more subtlety to this question actually because you have negatives. So any even number of as long as you have negative ones multiplied through in a way that they cancel out to make the answer positive, that will work. So one way you can think about this is you can assign each of the first y minus 1 items a random sign. Or not random, but you can choose it however you want. And then the last one's sign will end up being fixed by the previous ones. So for example, if you have y equals 8 and you set the first 7 y's so that 3 of them are negative, then the last one has to be negative to make the total product positive. Cool. So this ends up being the answer. Let me make this a little smaller. All right, let's code that up. And here our numbers go up to 1,000,000. So what we can do is we can find all the primes up to 1,000,000, and then we can efficiently factor all the numbers, because we do have to do a bunch of queries, but we can do the sieving first, and then we can do the queries. Okay, and then we also want to do this mod 10 to the 7th. Yeah, so we want to go to this is pretty nice actually. So this sieve library, which socket wrote, already has a really convenient method to factor your number. Super convenient. And then let's do our formula here. We're just basically just implementing this formula. And you'll notice here I did y minus 1 instead of choose count. It's the same. That's how binomial coefficients n choose k and n choose n minus k are equal. So let's try running this. I'll close my nice relaxing stream. You're doing a better job of explaining what you're doing than a lot of people who do coding streams. Yeah, definitely happy to hear that. Yeah, there are a lot of people. I think there are a lot of people on Twitch who just do coding streams where they're like hanging out and coding, and it's more kind of hang out with me and chill. And then this one is more of an educational focused stream, like a lot of the other ones that are competitive programming related. The programming is just for solving these problems, so explaining is a pretty essential part of it. All right, so let's submit this. And then, all right, cool. We got accepted. All right, so Kamil and making a stream. So this is a pretty tough problem. Now we're getting up to definitely the tougher ones. I actually just solved this one today before the stream. I know some people like to see problems for the first time on stream, which is also a really cool experience for viewers, but I personally like to try to make sure I'm kind of familiar with them at least, and then maybe figure out the details on stream, just to keep things moving. Okay, so this is kind of a complicated problem. Definitely going to make use of this whiteboard. And then I'll go through my code, which I just wrote this afternoon. So what we're doing in this problem, it's a pretty long statement, but basically you have a labeled tree. So you can see here you have a tree, and it's a little small, I'll make it bigger. The labels are these little numbers 4, 5, 6, 0, 8. And so you want to consider all the paths between a node and an ancestor. So this is like a path that just goes vertically in the tree. So this wouldn't include, if you imagine this being your tree, because it's the one that they drew. A path like this wouldn't be valid because it doesn't just go between a node and its ancestors. So you want to consider each of those and find the GCD of the things along those paths. So you can see here they had 4, 0, and 8, and the GCD of those is, well, I guess that's highlighted here. GCD of 4, 0, and 8 is 4. And then you want to find the sum over all those GCDs. So the naive solution to this problem would be to just consider all possible pairs. And of these, there would be, at worst case, n squared, because you could have a tree like this where every node has O of n ancestors. And so that would be an n squared solution, which would end up being too slow. So the kind of important thing to consider here is that as you go down the tree, like let's say you're at this point and you're going down further, you know that there are these 3 things above you, but you don't actually care what all of them are individually. You just care about the GCDs of each kind of suffix of them. Oh, Dhruv414, thanks for the follow. So you only care about the GCDs of the suffixes because those are the only things that you can actually extend by adding on an element. So if you consider kind of this one path going down from the top, and you consider the set of the GCDs of all the suffixes, to get to the next one, which I'll draw in blue, you have, actually, I'll draw them in the other order to start with. You have all the same things, but with this element added, or just this element by itself. Wow. Hey, how's it going? You wanna teach some number theory next? Yeah, so let's see, where were we? Cross hairline, thanks for the follow. So, by the way, actually, this reminds me, I thought you were doing programming contest problems. Yes, so this is a number theory related programming contest problem. So the theme of this stream, I'll post the link. The theme of this stream is that we're going through all these programming contest problems that are number theory related in some way. and then trying to cover the number theory behind them. So definitely fun for me, kind of a more mathy stream than usual. So yeah, okay, cool. So we want to maintain this set of GCDs of all the suffixes of our ancestor path as we traverse down the tree. And there's a key observation. Oops. Key observation. The set of So the key observation here is that the set of GCDs of suffixes can't actually have that many distinct values. And here's how we can see this. It's anime time for me. Have fun. Thanks, and enjoy your anime. So let's say your values going down the tree are A1, A2, A3, and so on. Then, oops. Then we have GCD of A1, GCD of A1, A2. Actually, I guess I reversed that. All right, so let's say your values going up the tree are as follows. And what's kind of cool is you can get this next GCD by taking the previous GCD and GCDing it with the next value. So this kind of leads us, so let's call this G1, G2, G3, and so on. So if we have GI and GI plus 1, then we know that this must be true, right? The GCDs can only decrease. And we also know that if the next GCD, since it's a divisor of the previous GCD, it's either equal to it, in which case we don't add any distinct values, or it's what was I saying? Or it has to be a divisor of it, which means that either GI plus 1 equals GI, or GI plus 1 is less than or equal to GI over 2, since that's the largest divisor you could get. Cool. So what this shows is since the maximum value here is 10 to the 12th, and you have the GCDs every time, the maximum number of distinct values would be is bounded by the log base 2 of 10 to the 12th, which is, I think, not that big. I guess it's around 40. Cool. So this actually leads us pretty directly to our submission, which I guess I don't have viewed publicly. All right. All right. So here, there's just some pre-written tree code. And then what we do here is we go through each vertex of the tree going downwards. And for each vertex, we store a frequency of how often all the GCDs or the suffixes of its ancestor chain appear. So I'll put this like that. And then what you do is you want to find their contribution to the final sum, which is the value times how many appearances it has. And then what you do is for each of the children, you want to see what the value at the child is, and then find its GCD with each of your values. And that gives you the map for the child, kind of using this this extending down the tree logic, but we're doing it along all the branches of the tree. All right, so let's just submit that. Since I think I submitted it earlier in like coach mode or manager mode or whatever. Cool. All right, accepted. So now we're going to check out product-oriented recurrence, which I don't know if second thread is still here, but he identified that problem earlier as potentially interesting. Cool. So here we have a recurrence, but it's kind of weird because you're multiplying stuff instead of what we normally do in a recurrence, which is we add stuff. Let me make this more readable. But basically, you have this recurrence, and you want to find some value that's super late in the recurrence, actually 10 to the 18. So we definitely want to do this pretty efficiently. Let's switch my pen back to black. So here's what we can do. So we're given values C, F1, F2, and F3. So, and all we're doing is we're multiplying previous values, and then we're also multiplying in more factors of C. So our answer, or actually instead of saying our answer, I'll just say f of x equals, let's say C to the, okay, px times f1 to the qx times f2 to the rx times f3 to the sx. So the reason for this is if we're just starting with some starting values and we're just finding products of them and then finding products of those products and so on, we can definitely express our final answer as some complicated product with potentially very high exponents of the original starting values. So now what we can do is we can consider each of these values completely separately, and we can just calculate the recurrences px, qx, rx, and sx. This is a little bit annoying to do, but it's definitely doable. For example, our recurrence relation for qx is qx equals qx minus 1 plus qx minus 2 plus qx minus 3. Because as we're taking this product, those exponents get added. And this is the, and same for R and S. And then the only complex one is px equals px minus 1 plus px minus 2 plus px minus 3 plus 2x minus 6, because we're also adding in these extra factors of C with every step. So what we could do is, given these two recurrences, or given these four recurrences, because we have P, Q, R, and S, we can express each recurrence as a matrix, where the matrix gets you from your current state to the next state. And then we want to advance our matrix n times. So we could use binary exponentiation to exponentiate this matrix. So that would take log n time times some constant factor for matrix multiplication, like probably something like 5 cubed, which would definitely run in time, but possibly be a little bit annoying to code up. Annoying, but not impossible. So I guess, should we go through the exercise? So we only have 2 problems left. We have this one, and then we have steps to 1, which actually is by far, I would say, the most exciting of these problems. I really, really liked it. So I'm trying to decide if I should code this or if I should try to skip to the more magical solution. How to find px? Can you clarify a little what you mean by how to find px? So px is given by this recurrence. And then the starting values, I guess, here recurrence relation contains variable x. All right, that's actually a great point. Let's go over that. So normally what you would do is, all right, so first let's do qx. So qx minus 1, qx minus 2 equals, we'll have some transition matrix times qx minus 1, qx minus 2, qx minus 3. So some of these values are pretty easy to find. Qx minus 1 is just equal to qx minus 1. So we can just get that directly. And then same with qx minus 2. And then qx is going to be the sum of all of these. So this would be our recurrence relation for q. Makes sense, right? So now there's this cool trick where what we're going to do is we're going to, whoops, I guess this should be p. px minus 1, px minus 2. And then we're also going to compute x, and we're also going to compute 1 using recurrence relations. Yeah, that's exactly right. So now we have px minus 1, px minus 2, px minus 3, x minus 1, and 1. So again, for some of these, so those are the easy ones. And then px, we know, is going to be equal to the sum of the previous 3 values plus 2x minus 6. So this 2 and minus 6 end up getting multiplied by, I'll zoom in a bit. Zoom in here. Cool. So hopefully this makes sense for how to find px. And now we just need to figure out how to do the bookkeeping to maintain x and 1 throughout this recurrence. So 1 is easy. It's just equal to 1. So we can fill in this row. And then x is going to be equal to x minus 1 plus 1. So if we do this, this will give the recurrence relation. So if we initialize our matrix with the initial values and then x minus 1 and 1, or I guess x and 1, then this transition matrix keeps track of 1 and x as well. So this is a pretty standard trick. It's definitely not that well known though, so it's pretty good to know because it allows you to, do things like this. Cool. So let's close our previous code, and I guess let's implement this. I'll make sure that's up. Okay. Negative. Isn't it -4? Um, I'm a little confused. Can you explain why this would be -4? Maybe I'm just missing something simple. If you do, let me know if you find any parts easy or hard to use. All right. Does sockets not already have a mod? Ah, okay. Yes. That's a great point. Actually, what I should have done, yeah, I should have done this a little differently. Um, that was a really nice catch. So yeah, I'll change this to a -4. Um, wow, okay. We have a super attentive viewer. Yeah. I think probably, given that this led to some confusion, a nicer way to do this would be to consider this being like x plus 1. That might be a little bit cleaner. But yeah, you definitely got to be really careful with your indices. All right, let's see if this matrix class is any good. All right, so Neil, I'm going to be using sockets matrix class, but let's see if I run into any issues, and then, you know, I'll reach out to you via the chat. Did you make all your templates yourself, or is this some library? So this is my library. But you'll notice here that it's a fork of Socket's actual library. I just made a couple small changes to it because there's a couple just places where I prefer a different function or different arguments or something like that. But the vast majority of the code has been written by Socket, and some of it I haven't even read probably, but I just use it. So yeah. Like this modnum class, I think Socket wrote all of it, uh, and I didn't make any changes because it was already so good. So yeah, let's. Okay, cool. So what we want to do for this problem is we have two separate transition matrices. I'll just make M our matrix of modnums class for short. So I guess let's look at our Jamboard. So our simple matrix will just be 3 by 3. And then we're going to want to set all of these to 1, and then this and this to 1. So I'll put that, I guess, over here. And then I'll change this to T1. I'll call this one T2. Yeah, I'll call it U. I don't know. I'll call this one T, and then I'll call this one S. Actually, I can just copy this. So all the ones here will be in the same place, and then we also want S0, 3 equals 2, S0, 4 equals -4, not -6. And then we want S3, 3 equals S, 3, 4 equals S. Okay, cool. So these are transition matrices. And then all right, cool. This lets you multiply by a vector. So now we want to do MNP, call it P1 equals n times. So if we start with n equals, so n is going to be greater than, so let's re-index things so that our initial state is where you have F1, 2, 3, and then we want to do 4, or we want to do n minus 3 transitions above that to get to, actually, I guess the nicest thing is to make it so that F1, 2, 3. Yeah, so we want that to become Fn, Fn minus 1. Okay, cool. So int n equal int n. Okay, so there's actually a bit of a trick here. These mod nums should actually be, okay, so we want to find the answer mod 10 to the 9th plus 7, which means that we want to find the mod of the exponents mod 10 to the 9 plus 6. I'll do it like this so it's really clear that we're subtracting 1. And then we would just have our starting array which would be okay, cool. And then auto PC equals s.pow n minus 3 times. So initially we have 0 for all the for how many C's are in all the answers. And then we want to make sure that we're initializing this correctly. So here, I guess we would want so I think this would work. And then we would want to multiply back in this is definitely a nice candidate for a loop, but you know. KBG, thanks for the follow. So let's try running this and see if we, didn't make any off by one errors. All right, we definitely made some off by one errors. So let's try printing what we got. Yeah, good call. That definitely should be a long, long. Which I guess they... so I would have passed the samples at some point and then submitted and got wrong answer if it weren't for you. Awesome catch. All right. So let's see. So they're saying we want F5. All right, let's try the easiest possible example, which would actually be F4. So for F4, yeah, so for F4, we have one of each of these things, which is correct. But then I guess our value here, we want 2 times 4 minus 6, which is 2. And here we have some negative number, which is definitely wrong. So I guess... Oh yeah, so I guess we should have started this. We should have done the same n minus 3 thing. And then I think we should start this one at 3. Yeah. Yeah, because here we're kind of saying what the state is going up to F3. Cool. All right, let's start running this. All right, so this passes the samples. So let's submit this. Cool. And then actually, so I recall for this problem, there was a pretty cool trick in the editorial, which I think wasn't really necessary, which made this problem easier than they expected. But you'll kind of notice that this 2x minus 6 in the statement is a little bit suspicious. Like, why 2x minus 6? And it turns out that that's because... nice, yeah, cool. So Mekdik, who definitely enjoy his contests, he wrote this problem, and there's this trick where what you do is you replace f of x with c to the x times f of x, and Oh, I see. So they actually did prime factorization, which is not necessary. But the cool trick here is that if you form it like this, you actually don't have to worry about the C's at all. So you can just replace all these values with that. So we can actually try that. So I think what we would want to do here is we won't even use this because that's only necessary when we have these weird C's. And then we would divide F1 by C, F2 by C times C. Oh, HM Vagasia, thanks for the follow. And F3. Oh no, I guess we want to multiply them? Hang on. F1 should be replaced with... Yeah, okay, so we want to find like this sequence. We don't need this anymore. That doesn't make any sense. And now we'd want to do answer. You can then divide answer by c.pow n. And I think this should still work. And this is a lot nicer because now you didn't need to do this complicated 5 by 5 matrix. Yeah, cool. So this still passed. I'll submit it for completeness. It should be slightly faster if the time actually mattered, which I'm not sure if it did. Yeah, good. They're both basically instant. But so the intended solution here was to calculate it separately for each prime, which is definitely a bit more work than what people ended up doing. The reason for this is that instead of doing each prime and then factoring all the f1s, you can just use the f1, f2, f3 as kind of fake primes and find the factorization into those, which isn't unique, but as long as you find a correct factorization, you can get the answer. Awesome. So let's do steps to one. Though I'm just gonna go grab a glass of water and I'll be right back. So stay tuned for the coolest problem of the stream. Steps to one. Edit command. And I'll just cool. Yeah, so I'll be right back. All right, I'm back and we're ready to do steps to one. And then I think somebody else had a leak code problem they were interested in, so happy to go over that quickly after this. Cool. I'm back. All right, so this is a pretty cool problem. Clear frame. Okay. L, steps to one. All right, so what we're doing here is we start with an array and some constant m, and we pick random numbers until the GCD equals 1. And this process will terminate eventually because eventually you'll get to 1. The GCD will always be decreasing or staying the same. So they have some examples here. The second example is a good one. So you basically append numbers that are in 1, 2. And you stop when the GCD is 1, which in this case is when you hit your first 1. So you can imagine it would be like 2, 2, 2, 2, 1, and then answer equals 4. So you can see here that this stops when you hit the first 1. So the expected value is 2. And in general, if you have some process that succeeds with probability p, then the expected number of steps is going to be 1 over p. And that's going to be an important fact later in our solution. So yeah, in this case, which is the simplest case, well, other than this, where the answer is just 1, you just stop. Cool. All right. So let's think about another case. Let's say m equals 6. Then you could have some array. Let's say you append 4, then you append 6, then you append 2. The GCD here's, or the GCDs are 4, 2, 2. And then let's say finally we append 5. And now the GCD becomes 1 and we stop. So that would be an example that's length 4. All right, so as has been a really common theme for, I guess, all our problems today, what we want to do is we want to consider all the primes that could go into our number or our GCD. And we look at each of the primes completely separately. So let's first look at the 2's that we have inside of this. So this would be 4, 2, 2, 1. And then if we look at the 3's, it would be 1, 3, 1, 1. And if you looked at the 5's, it would be like, 1, 1, 1, 5. So what we can do is we can find the length for each prime where that prime becomes 1. And the answer is going to end up being the maximum of all of those. Cool. So there's another way to look at the expected length of a sequence. And it's to look at it as the sum of a bunch of indicator variables. So let's say I roll a die 1 to 6 until I get 6. What? Wow, okay. I can't believe I misspelled length on stream. Oops. Okay. Oh, I actually didn't because I was showing the wrong slide. Actually, perfect. So, all right. So there's a cool way to look at this. So the expected value of x, this is the normal way to look at it, is the sum of I equals 1 to infinity of I times the probability that x equals I. So this is the standard way to compute expected value. You look at each of the outcomes, you find the probability of each outcome, and you multiply them together, and then you sum over all the outcomes. But there's a cool way to do it, or a way that I think is cool, which is for I equals 0, you sum the probability that x is greater than I. So let's look at an example. Let's say the length, which is x, is equal to 4. In that case, you have here, 4 on the left. That makes sense. But on the right, what you have is 4 greater than 0? Yes. Is 4 greater than 1? Yes. Is 4 greater than 2? Yes. Is 4 greater than 3? Yes. And then you have a bunch of zeros. So these two expressions are actually completely equivalent. And this one on the right is definitely a bit friendlier in a lot of cases because you don't have this annoying factor of I that you have to multiply through. All right. So now that we've done that, let's try to find probability that you have something that's greater than, I guess, what should our value be? Probability that x is greater than n. Cool. So we want to find the probability that x is greater than n for some n that, just for some variable n. So in order for x to be greater than n, we need means GCD of first n elements is not equal to 1. Oh, actually, John raised a great point. Yeah, the reason that it is actually often nicer, I kind of just said this quickly, but yeah, it's usually easier to find the probability that you get past a point than it is to find the probability that you get to exactly that point. And that is the main reason. Okay, cool. So, I'll put an R there. So it's clear we're talking about probability. So what we want to do now is we want to consider all the possible primes. So for GCD to be greater than 1, we need a prime to divide all elements. So for a given prime, let's call it P, what's the probability that the prime divides all the elements. So the number of primes that we have here, or sorry, the number of elements that we have here is m. So the number of prime values would be, or sorry, the number of values that are divisible by p would be the floor of m over p, and then that divided by m. So let's let r equal to this. Then what we end up doing is the probability that you get to n things would just be r to the n. It would be the probability that all of the first n elements are from this set of the multiples of p in your range 1 through m. So here is the final way to combine these. Sum over p of, oh, I guess I don't want to write r like that. I'll just write the actual thing. Ghost 101, thanks for the follow. I'm at 198, so we might be able to get to 200 in this stream, which would be awesome. Maybe I'm at 200. I should know to see. Actually, I don't know if people are unfollowing me because it's someone else just followed Anikatel 2000 and it still says 198. Oh, now it says, wow, I'm at 200 followers. Awesome. Super, super gratifying to see. Nice problem set, thanks. Yeah, this is definitely a fun one. There aren't that many number theory problems on Codeforces, but I feel like when I do see them, some of them are really cool. Anyways, so the astute viewers out there might notice that there's something wrong with this. And the reason is this actually ends up overcounting things because this finds the probability that this is adding up the probability that your GCD is divisible by 2 and the probability that it's divisible by 3, 5, 7, etc. But it actually could be divisible by 2 and 3, in which case we're overcounting. So we actually want to subtract the sum over P1, P2 of M over P1, P2 over M. And so on. So this ends up actually, this is basically inclusion, exclusion, which I will Google. Hopefully this Wikipedia article is clear. So yeah, the most clear version of it is A union B. It's A plus B minus A and B, or the intersection of A and B. And then when you have multiple sets, you have to subtract all the even numbers of sets that you're unioning and then add back in all the odd numbers. So this would continue to just alternate. I don't know if they have a summation written out here. Yeah, they do here. They have, this negative 1 to the n that appears. So what we want to do is we actually want to look at, hey, AOE person, good to see you again. Yeah, what we're doing right now is we're going through the last problem from this mashup. Definitely the coolest one, but maybe one of the most complicated. There's a few steps in the solution. Plus, etc. So if you pay close attention here, what what you want to do is you want to look at all the possible products of distinct primes that are less than m. And if it's an odd number of primes, you want to add this value. And if it's an even number of primes, you want to subtract this value. Yeah, and that would be only for the products of distinct primes. So if odd number primes, you want a plus, even number, excuse me, you want to subtract. And if it has a repeated prime, we actually don't want to do anything. So it turns out this is actually something called the Mobius function. Excuse me. So the Mobius function is 1 if you have an even number of primes, -1 if you have an odd number of primes, and 0 if you have a squared prime factor. So this is the negative of the Mobius function. And this makes sense. Hey, can't be shown. Glad you dropped into the chat. So, oh, whoops. Next slide, please, to myself. So this is the Mobius function, or the negative of the Mobius function. And you don't actually need to know about the Mobius function to solve this problem. We're just solving it kind of from first principles here, but there's definitely a relationship between our solution method here and the Mobius function, and I think Mobius inversion. Cool. So what we want to do now is we want to compute the sum so to find the probability that x is greater than n, it's going to be equal to the sum from I equals 1 to m of the Mobius function of I. I kind of drew a pretty gross mu there. I'll try again. I guess the negative Mobius function of I times this quantity that we described before raised to the n. And then what we want to do is we actually want to sum these. So this is all well and good so far. We have a nice, like, finite sum. We can probably figure out how to compute this efficiently. But we actually, if you remember, want to sum this from n equals 0 to infinity. So here things get a little tricky. But luckily we can interchange this summation. Draw an arrow up here. Actually, I'll just draw it down here. Oh, Eval Pras and Shep MD1, thanks for the follows. So if we interchange the summation, I equals 1 to m. Oh, we can bring the Mobius function to the outside because it only depends on I. Then we have the sum n equals 0 to infinity of m over I over m raised to the n. And this is a pretty simple, 1 plus r squared plus so on equals 1 over 1 minus r. I wrote this a little small, but so now here's where I'll draw my arrow. So now this is going to be equal to the sum from I equals 1 to m of negative Mobius function of I times m over I over m. Whoops. All right, cool. Now this should just be our final answer. Definitely what I consider kind of a cool solution. It had a few different tricky steps. We can go over them briefly. So I guess first you want to know that this trick of replacing this expected length with a summation of the chance that we get to each point. Then we want to do this inclusion exclusion over the prime factors. And then finally, we want to be able to interchange the summations so that we get this nice thing that we can actually compute because it's a finite sum instead of an infinite sum. So let's try coding this up. Try to figure out the input format. So m. Okay, cool. So that's pretty simple. M is just all we have there. So now I will put the code over here on this side so we can still see our whiteboard. So first, let's compute our Mobius function for all the numbers from 1 to m. So let's see. Okay, so we can compute this, I think, the most direct way. Cool. So here we're just going to prime factorize our number. So first, if our number has a square in it, then we just immediately want to stop because there's no sense in, because the Mobius function there would just be 0. We don't want to use it in our inclusion exclusion. Kind of forgetting about the Mobius function and thinking about inclusion exclusion, we don't want to use it. Then we would want to negate mu. And then we want to divide out the factor of d that we have. So I think this will get us all the primes. Yeah. And then now we want to compute this ratio r. So r equals 1 minus. So here we want to do floor division of m over I, but then we want to convert it to a mod num to actually do this division by m and then do 1 minus that. And then, so I guess this would be r. And then we want to do answer plus equals negative mu times 1 minus r inverted. And let's try running it. Okay. So I think the problem is we don't want to start with I equals 1. Yeah. All right, so there's clearly some kind of implementation error here. Okay, right. We want to skip the things that aren't actually factors at all. Like, right, so here I think I actually just counted the parity of I or something instead of the number of. This is a slow way to compute mu. I think it's fast enough for the purposes of this problem. But yeah, so there is a way to compute. There is a way to compute the Mobius function from 1 through m in, I think, just linear time using a sieve. So maybe I should do that, but I am kind of curious why this implementation is wrong. John, do you see the bug here? Oh, I see. I think. Okay, well, first of all, I shouldn't be changing I here. That's kind of a no-no when I have this loop. I don't even know how this like works at all. Um, and then I think here, if v is greater than 1, we want to do this because there's one last prime. Oh, shoot. Thanks for the heads up, John. I guess that was the reason why I didn't have the code on that side. Let's see, let me make this whiteboard a little smaller. Okay, so now I think everything should be visible. Um, Interesting. So it appears that I have a tiny mistake. Or it looks like a tiny mistake, but maybe it's not. Um, let's try this. Let's see if we compute the Mobius function correctly. All right, so for 2, it's -1. Oh, I guess I want to initialize this at So for, I guess, it's not that important to get the Mobius function right, but let's just try. All right, so if it has an even number of prime factors, we want it to be 1, so we should start this at 1. And then the values of mu look correct. All right. Um, but the output is wrong. So maybe there's something wrong with one of these formulas. The output is right for one of the cases, which is a little weird. Yeah, so for 6 we have 1. For 10 we have 1. Yeah, it seems legit. Then for 17 we have -1. Okay, yeah, so those look correct. Hmm. So I think, do you handle I equals 1 correctly? So do I not want to just skip I equals 1? I didn't want you to derive it, but it seems to explode. Oh yeah, so I guess I'll quickly recap the derivation. So the thing that we're doing here is we're doing inclusion exclusion over all the primes. So we want to just skip I equals 1. I believe we like don't care about it at all. Yeah, is this M over P correct? Um, so I think I have a mistake somewhere in one of my summations. So this is the probability. So the probability that you have at least one element is going to be 1, which is going to be r to the 0. Okay. So I think you always have one element. So I guess the question is, does this summation handle that correctly? So I think the sum of the Mobius function from 1 to m should be equal to zero, so that doesn't matter. Hmm. Now let's look at what we're outputting. All right, let's just try the example where the only prime is 2 to try to follow through our derivation. So we want to end up, cool, and this gives the wrong answer for that. So clearly we have some work to do. All right, so when you only have one prime and that prime is equal to 2, the probability that we, let's see, the probability that we keep going after a given element, after n elements, the probability that we get past that, leaf me, thanks for the follow. The probability that we get past the first 0 elements is 1. The probability that we pass the first element is 1/2. But somehow we're not even printing the right answer for that. So yeah, so R here is 1/2. I think this is 1/2. Yeah, this is 1/2. So 1 over 1 minus 1/2 is 2, which is correct. I think clearly something's wrong here. So we have 1 minus R. Is it possible there's some weird order of operations? That can't be it, but in fact, that won't even matter because inverting R doesn't actually really do anything. But wait, 1 over 1 minus R is 2. So mu is -1. All right, that's fine. So we have 0. No, we have -1 times 2, which is -2. Oh, so I think I just have negative of the answer. Right, so I don't actually want... So I wanted this, right? I forgot about that. But we're still failing some samples. Can you please share recording this stream? Yeah, so all my stream recordings will end up on YouTube on this channel. You can check it out and subscribe there. And typically when I upload them, I'm going to try to put like timestamps and stuff, so it'll be really easy to find the part of the video you want. In as much as there'll be a timestamp saying, this is when I discussed this problem, and then within that, you'll have to, search yourself. Yeah, and thank you. And yeah, be sure to follow me here and subscribe on YouTube if you haven't already, so you can stay up to date on my content. All right, so now we passed that sample, which makes sense. But we're having some problems here. So 2 gives you correctly 1/2 as R. And then 3, we should be getting 3/4. Um, and then 1 minus 3/4. Oh no, we should be getting 1/4. Then we should be getting 1 minus 1/4. So this number should be 4/3. And it is. So that's 4/3. So the answer should be 2 plus 4/3, I would think. I'm getting a pretty different formula. Which part are you getting a different formula for? You need to multiply 1 over 1 minus r by the cumulative sum of ux 1 to floor m over d. So all right, I'm not doing advent of code today. I'll just try to wrap up this problem. But okay, so John is explaining the cumulative sum. John, where did you get that? Or I guess like how? No, maybe not how. Yeah, but like how did you get that? Did I make a mistake here where I interchanged the summations? The sum of ux from 1 to floor m over d. What's the probability? So I think my derivation is pretty simple, John. Let me quickly outline it for you, and you can tell me what's wrong. So for each prime, in order to have to continue past a point, you need all the numbers so far to be divisible by that prime. So that's where I get this floor of m over p divided by m. So for example, if m equals 4 and p equals 3, then you only have a 1/4 chance of each number being a multiple of 3. And then you want all of those elements so far to be a multiple of 3. So that's r to the n, where r equals this. And then you want to do this inclusion exclusion. I guess. Oh, hey, demoralizer. We just got to the Mobius inversion problem. If you're just tuning in now. So yeah, it makes sense. This is at a pretty early time for your time zone. So let's see. I feel like there's some issue where this is wrong for when you have no elements so far, but maybe not. So if you just add up the sum over all the primes, where you have n equals 0, what do you get? You get yeah, I think this is wrong for n equals 0. So I think what we can do is we can just start from n equals 1, which would make our summation be this r over 1 minus r. And then I think we can add 1 at the end. Oops. Okay. So now this passed. So I think there was some like issue with my logic here doing this summation. Yeah, I guess the thing is if you have 0 elements, then there's no need to stop at primes. There's no need to only go through the primes that are less than m, right? Like you're kind of taking like 0 to the 0 for a bunch of these terms, so it doesn't really make sense. So what we want to do is we can go back to this slide. I'll kind of mark this up in red, like a little grading. We can actually do 1 plus, and then we can start this at 1, assuming that we always get past 0. And then when we fast forward a bit, we have 1 plus, and then this starts at 1, 1 plus, this starts at 1, and then plus, so originally here we had 1 over 1 minus r, and then here we want this to be r over r, 1 minus r. So now this passes, so we can submit this. Cool. So we got accepted, and then yeah, I think. Does anyone have any questions about? Oh, and I'll ask again the thing that I asked earlier about the beginner contest because I'm definitely curious whether people would be interested in it. Oh, I forgot to go to the next slide here. Yeah, so here we have 1 plus, and then here we have r over 1 minus r. Because we want to start the summation at 1, at n equals 1 instead of n equals 0. And then we end up with this correct code where we compute this Mobius function, and then we have this minus r over 1 minus r. And then here we just do plus equals 1 at the end. Pretty subtle bug to catch. And then let's see if CodeMonkey is still there. Let's see if he has the link. And then I'll state this again. Cool. Yeah, and does anyone have any other questions about anything number theory related that they'd like me to try to go over a little bit, or any other number theory problems? I'll cover that. If not, I'll probably wrap up the stream. Cool. And I'll be back in like 1 minute, 1 or 2 minutes, and if nobody has any uh, yeah, I'll probably end the stream if no one has anything specific to cover. Okay, I'll be right back. Great catch. Yeah, my sound was muted. Okay, I'll just repeat everything I just said. I'll go back a little bit. So Pranav asked, how do you approach number theory problems? And for that, I'd recommend checking out the past 4 hours of this broadcast where we approached a bunch of different number theory problems. Super fun ones too. And Long Contest asked how to compute some summation. And I'm not really sure, but I'm going to take a quick look at it. And then C Films asked, how are you doing? And I'm doing pretty well. Had a fun stream so far. And C Films also asked, what is number theory? So number theory is a branch of math that's stuff like modular arithmetic. Basically, it's stuff relating to integers, like primes, factorization, divisibility, things like that. So for this sum, so so you can rearrange this. The other one. And after you do this rearrangement, you can set theta such that sine theta equals x over square root of 1 plus x squared. And then cosine theta equals 1 over square root of 1 plus x squared. And then this is square root of 1 plus x squared to the n times cosine theta plus I sine theta raised to the n plus cosine theta minus I sine theta raised to the n, which is 1 plus x squared raised to the n times e to the I n theta plus e to the negative I n theta. It's modulo p and x is an integer. All right. What's the source of this problem? I assume you didn't just make it up randomly. So, can you link to the original source? C Films asks, "What is Jamboard? Do you do programming?" Yeah, I do a lot of programming. I program as my job, and then I also do programming competitions recreationally. And there's some code there. And if you check out my stream, it's in Hacker Earth Circuit. Yeah, please post the link. But let's try seeing where this goes and seeing if this gets us to the answer. Summing the weird series. Oh my gosh. Okay. What the heck is this? All right, so I see that you transformed this problem into the other problem. What the heck? 3k squared to the t over 2. The inner sum became that. So typically, if you have like a million sums, you don't just want to evaluate the inner sum and then the second inner sum and so on, because a lot of the time that'll be like complicated. Um, this seems like it's a pretty hard problem because almost nobody has solved it. Let's see. So we should probably try to think about this problem combinatorially. At least that's my guess. Uh, that that the objective here would be to figure this out combinatorially rather than like analytically, I guess, is the alternative. So let's think about what we're doing. So first, we're picking our elements. Oh, B noob followed. Awesome. Welcome to the club. So first we're picking our elements, then we're picking of n, s of r, pick t of s, then pick 1 of t. So this would be n choose r, this would be r choose s, this would be s choose t, this would be t choose 1, which is just t. Then we want to, I guess we want to multiply by this weird number, 3k squared raised to the t over 2. I'm pretty sure that's just 3k to the t. So, and I don't know why there's a, oh, 3k, yeah, 3k to the t. So now then color the t elements, 3k colors. So for each of the t elements, you have 3k colors that you could give it. Then you have to multiply this weird factor, which is based on how many elements t you picked, and then divide by this other weird factor, which is how many elements s you picked. Oh, yeah. Yeah, that should be a square root 3. Good catch. So I'm not really sure what to do next because I don't know an obvious way to combinatorially interpret the next two things. I guess t has to be odd. No, t has to be even is what they're saying. And you want to... Okay, so let's actually try replacing t with 2t, because I think... Oops, that's some weird handwriting. So now you want to multiply... You want to multiply by -1 to the t. This one I don't really know why. And then you want to divide by s plus 1. And that, again, I'm not really sure what we want to do. So we can think of this as you have elements of n that aren't in anything. Then you have elements of n that are in R but not S. Then things that are in S but not 2t. And then you finally have this picking one of the 2t elements specially. And then you also have coloring the 2t elements. So if you imagine coloring things, we have one color, one color, so maybe we can think about this like coloring all the elements. So let's make a list of colors. So not in any, in R, in R and S. And then in R and S and 2t. And then this is actually square root 3k colors. So I'm actually not sure where to go next, but it kind of feels to me like this is likely on the right track. Well, actually, I can't even say that for sure, but it seems like we're kind of getting somewhere potentially. But yeah, I'm not sure. I'm definitely interested to maybe work on this problem some more, or read the editorial, or get a hint from someone or something. But I think for now, it's getting a bit late, and I think I'll wrap up the stream. Yeah, if anybody has ideas for a future stream, definitely let me know. You can message me on Codeforces. I guess before I wrap up, I'll plug my YouTube. Definitely follow here and sub on YouTube. Long contest says counting. Is that a suggestion for a future topic? I definitely want to do a future stream on combinatorics and expected value. So if that's what you mean by counting, then that's definitely kind of already on my radar. That's one of my favorite topics, so that would probably be the next stream. or the next topic-based stream, I guess. I'll probably do some low-key problem-solving streams in between. Sort of thanks for the follow. Cool. So I think I'll end the stream here, but definitely excited for the next one, and I may be able to do a stream after @coder tomorrow, but I think I probably actually won't be able to, just because of the way my schedule works out. But thank you so much, everyone, for joining, and staying with the stream throughout all these problems. Actually, before I end, yeah, expected value, I really, really enjoy, and also, I think it's also pretty interesting because I think there are a lot of combinatorics problems where if you think of them as an expected value problem, it makes the code and the reasoning a lot clearer. Like when they tell you to sum something over like all permutations, instead I like to find the expected value for one permutation and then multiply by n factorial at the end. And that example was a little bit trivial, but I think it helps a lot with reducing some casework. User plus number. Nice username, very formulaic. Thanks so much for the follow. Definitely curious to see if people did any, I guess status is where to look. Do some @coder virtuals. Yeah, I'm glad somebody likes my editorials. I'm actually curious if people did a lot of problems just while I was streaming. Awesome. Yeah, it looks like a lot of people did keep plugging away at this contest. That's super cool to see. All right. Cool. Thanks so much, everybody. I'm gonna end the stream, but thanks again for joining. I definitely had a lot of fun. All right. Bye, everyone.